first thing I want to kind of look at in this section is kind of remind you of what you learned in trig. You learned what we call circular trigonometric functions. Well, somebody had this idea that we, instead of basing everything on a circle, like you do in trig, we could base everything on a hyperbola. And we end up calling that hyperbolic trig functions. You could make a whole class out of that. I mean, if you wanted to. I mean, and sometimes in graduate school, people might be interested in researching areas like that. Somebody just had the idea. It turns out that it has lots of kind of interesting applications. So, for instance, I think I talked about didn't we do a problem like on the St. Louis Arch or something? And I said that was a catenary. You know what a catenary really is? Okay, say like you have a couple of telephone poles. And basically the wire sags. Okay, that's called a catenary. It's not a parabola. It kind of looks like a parabola. It's actually a catenary. And it turns out those things are represented by hyperbolic trig functions. Okay, so anytime you kind of have a sagging thing, and that actually has a lot of applications in engineering, because you have lots of cables and stuff you're looking at forces on. So those of you who are going to be engineers, you'll deal with this hyperbolic trig stuff here and there. It just kind of shows up. Catenaries is kind of the application that I know something about. So the idea is, first of all, to begin with this, I want to just kind of look at the circular trig functions, and then we'll kind of begin to get into the hyperbolic here. So these are the basic things you learned in trig. You have a unit circle. So remember what you learned is you learned that x squared plus y squared is equal to r squared, but in a unit circle, r is 1. That's the Pythagorean theorem is what that is. You also learned that in a unit circle, the cosine is the x value, the sine's the y value. Now I'm using t to represent the radian measure of an angle, okay? So the thing on this is a little more than what you learned in trig, but the idea is t can be thought of in three ways. First thing what you learned in trig is it's just the angle in radians. The other thing that t can be thought of is t is actually the arc length right there. One way to kind of help you remember this, if you did this in like high school geometry, I mean, you may have learned that if that's 30 degrees, that arc is also 30 degrees. You can measure them the same way. So if you have a unit circle, if that thing was like pi over 2 radians, then the arc length would also be pi over 2. They're the same thing. Okay, so it's the same idea. Now, one thing that you probably didn't learn in trig is also the area of this sector is really, t is also turns out to be 2 times the area of that sector. And I'll show you why that is. It's pretty easy to show why that is. But just remember that the angle in a unit circle turns out to be the same thing as the arc length, that it subtends or that it intersects. Now, what you can kind of do on this, I want to just sort of talk through what we do here just to show you where this thing comes from. Okay, the idea is what you would have learned in trig. You probably may remember learning that formula. That's the formula for finding the area of a sector. Does that look familiar? Okay, if you took trig, I mean, it's easy to forget that stuff, but we teach that in a trig class. That's the area of a sector. Well, in a unit circle, see, r is 1, so we plug a 1 in there, but theta is also t. Theta is just, in my diagram, going to be the same thing as that angle. So I'm going to replace that with t, so you would have a, the area of this sector would be equal to 1/2 times 1 squared times t, so that would be a equals 1/2 of t. Then if you multiply both sides by 2, you would get the fact that this angle t is twice the area of that sector. So that's where that comes from. So the idea is, in a unit circle, and this is a unit circle, which is important on that, if this was, I don't know, if that was pi over 6 radians, then that arc right there would also have a length of pi over 6, okay, like that. And then the other thing on this is that would be twice the area of that sector. So pi over 6 would also be equal to twice the area of this sector right there. Does that make any sense? Okay, that's the idea. And another thing that could help you a little bit to understand this part is S is equal to r theta. That's a formula for arc length. Well, look at this, okay? S, in unit circle, r is 1. What's theta? Theta is pi over 6. See what I mean? They're the same. That's the beauty of a unit circle, is the angle is the same as the arc. Does that make sense? Okay? So we have to kind of get that idea in our mind when we go to the idea of a hyperbolic function, which is the next thing. So somebody just had this idea. Okay, let's try a circle. I guess you could probably do this maybe with an ellipse. Maybe you could do it with other types of curves. So hyperbolic trigonometry is no longer based on a circle. It's based on a hyperbola. So the first thing that you got to kind of be solid with, and a lot of times students don't have real good backgrounds for conic sections. We do them in college algebra, but we don't spend a whole lot of time on it. So generally a hyperbola looks like this. Basically, the general thing is x squared over a squared minus y squared over b squared is equal to 1. That's a general formula of a hyperbola that has a center at 0, 0. That's the idea of a hyperbola. So what I want to kind of do is I want you to just watch this. You don't necessarily need to write this down, but I want to give you just a super brief review of what a hyperbola looks like. Now I'm going to look at a special hyperbola. I'm going to look at x squared over 1 squared minus y squared over 1 squared is equal to 1. I'm going to show you how you graph this. If you take college algebra, the way I teach people how to do the hyperbola is to do this. You have a center at 0, 0, and then all this means right here is this is a x-intercept. So it means you would go over 1 like that and put a dot. Same thing here, that's like a y-intercept. So you just kind of go like this. This is at 1, that's at -1, that's at 1. This is -1 like this. And then what I teach students to do is draw a little box around that, like that. Then what you do is you draw asymptotes like this. And then the sketch of a hyperbola looks like this. It's centered around that point, then it approaches those asymptotes like that. That's a very, very super fast review of what hyperbolas look like. Okay? In college algebra, if you took it here with CCD or somewhere else, you probably learned how to graph things at a very fundamental level. So this is what we're looking at in hyperbolic trigonometry, is we're really basing it on this hyperbola right here. The x squared over 1 squared minus y squared over 1 squared equals 1. So this is what it's all based on. Now, if you compare that with circular trigonometry, well, the key thing was this. X squared plus y squared equals 1. And that's the Pythagorean theorem. This is kind of like the Pythagorean theorem in hyperbolic geometry. Okay, so that's kind of how that works out. So it comes from that basic idea of how it works on hyperbola. Okay, and then what we do is this. Our points are cosine and sine, but we have an h that stands for hyperbolic. So that cosine h, it really stands for hyperbolic cosine, hyperbolic sine. And you'll hear me call it the cosh, and you'll hear me call that the sinh. Okay, it's easy, so it's a sinh. Okay, that's how we call that. Okay, then we have the tanh and the sech, and it just sounds funny the way we say that. Okay, that's just kind of the abbreviation. So if you see cosh and sinh, that means you're dealing with hyperbolic functions now. Okay, and it all works the same way. Is t just represents twice the area of that hyperbolic sector, just like t represents twice the circular sector in circular trigonometry. So that should give you kind of a rough idea. Okay, so let me show you this thing real quick. Let's see, I think this is a nice little GeoGebra thing that I found. And this is, I'm going to do 2 of these things. This is circular trigonometry. I think these things are so cool. Didn't have any of this stuff when I was a student. Okay, so here's circular trig. Okay, that's very easy, okay? When I go around the circle, what's basically going to happen on this is it's going to trace out the sine wave for me like that. Okay, I'm just going around the circle, and what all this application is doing is this. The sine is the y value, right? So right now, at this point in time, at this angle, which is somewhere around 3.5 radians, then this thing right here, the y value is 0.59 like that. So this is doing a sine wave like that. So all it's doing is plotting the angle and plotting the y value right now. So right now this is at 2.5 radians, and it has a y value like that. And as I continue to go through that, right now, see I'm at about 2 pi, so I'm to 0 like that. So that's what a sine wave is it just comes from the y values on a unit circle. That's what you learned in trigonometry. Okay, if I do a cosine, same idea. If I trace around the cosine, now what's it doing? It's just plotting the x values like that. So for instance, when you're at this radian angle, which is over here, it's plotting the x value. That thing is up 0.78 like that. Okay, does that make sense, kind of what it's doing? Okay, you learned how to do these graphs, obviously, but they're just coming from the values on a unit circle. Okay, so the way it works in hyperbolic, which is a little harder, I think, to see on here, but I'll just give you one example on this, and you can kind of play with this a little bit and look at this, because I have this link on my notes on D2L. So it kind of goes like this. Now you're looking at a hyperbola. So what I'm going to do is I'm going to trace out the graph, first of all, of the hyperbolic cosine. And what it's going to do on this is it's going to do kind of like what we did in the circle. It's just going to be taking whatever the value of t is, which could be thought of as twice the area of this hyperbolic sector in here. That's going to start plotting it out. So all I want you to do is just kind of see visually what's going on. It'll take a minute for the cosh to start coming up. Okay, it'll start graphing it. So you see those dots that are coming out, it's plotting the hyperbolic cosine right there. And that's kind of sort of looks like, almost like one of those catenaries I was talking about, kind of like that. So that's what the graph of a hyperbolic cosine looks like. That kind of has that U shape like that. And it's doing essentially the same thing that I did on that circle. It's way harder to see, but it works the same way. Okay. Now let me show you what a cinch looks like. So now this red one right here is going to be the hyperbolic sine. So it starts tracing that out, and again it's just looking at whatever t is and whatever that y value is on the hyperbola like that. Okay? All I wanted to do with that is give you guys a rough idea that they're doing the same thing. Does that kind of make sense? I'm not going through all the little details of that, but if you want to play around with this link, it'll help you, I think, to understand that a little bit better. Okay, so what I want to kind of get to next here is just kind of introduce some of the basic ideas here. We're not going to do much with this other than try to get the basic idea. So there's a couple of things that we want to look at here. Okay, so to begin with, the hyperbolic cosine is just the x value on the point on the hyperbolic, on the hyperbola, x squared minus y squared equals 1. Okay, so when I was doing that trace, that's what it was doing, is it was finding the x value on that hyperbola at a certain point. Hyperbolic sine is the y value on this hyperbola, like that. So that's the idea. All right, now, these things can be derived. I usually in Calc 2, it's a little timely to derive these things, but if you're interested, you could probably look it up and see where this comes from. But what you want to remember on this is the hyperbolic cosine can be written in terms of the exponential e. So the cosh is e to the t plus e to the negative t over 2. The sinh is e to the t minus e to the negative t over 2. Okay, that's something that can be derived. I don't derive that for you in class, but you want to get familiar with that. And really in this section, that right there is what you got to remember. Okay, that you got to study and remember those definitions. They're very close to each other. The sine has the minus, the cosh has the plus in it like that. Okay, and what we can do on this is we're going to derive a couple of other things on here. So again, the attitude is try to remember these, and then everything else falls from it. Okay, so if you need to work with the tanh or the coch, that always sounds funny to me, then you can derive them. Okay, so the idea on this is this would be what the tanh is. This is what the hyperbolic cotangent is. This is what the hyperbolic secant is, and that's hyperbolic cosecant. I don't remember those. I just figure them out as I need to. Okay, I remember the first two. So let's go through and let's do a couple of derivations that are real simple on these. So what I want to do first of all is just kind of do this like this. Let's do a derivation of the hyperbolic tangent. Let's do that. And then let's do quickly a derivation of the hyperbolic cotangent, because you want to know how to do this, okay? Well, first of all, one of the cool things about hyperbolic trigonometry is a lot of the identities are the same. Not all of them, but a lot of them are. So you know that the tangent is the sine over the cosine. Well, in hyperbolic, it's the sinh over the cosh. So it works like that, okay? So we have that. Well, the sinh, if you look at your definitions up here, okay, the sinh is this thing. So that would just be e to the x minus e to the negative x over 2. The cosh is going to be this. That's going to be e to the x plus e to the negative x over 2. Like that, okay? Then what happens is, of course, the 2's just cross out, and then you have your expression. So you would end up with this thing right here. You would end up with e to the x minus e to the negative x over e to the x plus e to the negative x, like that. Okay? And that's what I just was trying to show you the derivation of. Okay? So you do that. And you know, we're going to work with looking at the derivatives of hyperbolic trig functions. You already know how to differentiate e to the x's. So if you find the derivative of hyperbolic functions, you work with these exponential forms, okay? Next one's almost the same. You can just do this. This one just goes cosh x over sinh x, like that. So the cosh is going to be e to the x plus e to the negative x over 2. The sinh is e to the x minus e to the negative x over 2. So that crosses out. Then notice it gives this thing right here. Okay, so that would be the idea. So you can do that in your head too. All that happens is the 2's cross out. Okay, so that's what helps me to remember what the tangent, sinh, and hyperbolic cotangent are. Okay, everybody follow that okay? All right. Okay, so let's see. Let's do the hyperbolic secant and the hyperbolic cosecant. So if you want to do the hyperbolic secant, okay, it works this way. This is by definition. The hyperbolic secant is 1 over hyperbolic cosine. So all that really means is you would just do the reciprocal of the hyperbolic cosine. So the hyperbolic cosine, it gets replaced with e to the x plus e to the negative x over 2, like that. Now see, all you're doing is the reciprocal. So the reciprocal would be 2 over e to the x plus e to the negative x, like that. That's what hyperbolic secant is. All right? Take a reciprocal, just like you did in trig. Okay? Hyperbolic cosecant, by definition, is 1 over hyperbolic sine. Hyperbolic sine is e to the x minus e to the negative x over 2. So when you do the reciprocal of that, you would just get 2 over e to the x minus e to the negative x, like that. Okay, very, very easy derivation. Everybody see what I'm doing okay? So the thing is, if you just remember the hyperbolic cosine and hyperbolic sine, everything follows from it. So that's kind of the attitude that you want to take. So let's finish up, I think, with just this last thing here on this page. This is kind of a big deal in hyperbolic trigonometry. In circular trigonometry, what did you learn? Sine squared x plus cosine squared x equals 1, right? Okay, so let's just go through and let's do like kind of a quick little proof on this one here, okay? So what I'm going to do on this one is I'm going to write this as this. The hyperbolic cosine is e to the x plus e to the negative x over 2. Then I'm going to bring down the minus. And then the hyperbolic sine is e to the x minus e to the negative x over 2 squared. Okay, we're just going to crunch out the algebra. I'm going to do this fairly quickly So I'm squaring each term like this, okay? Now I'm going to just square these binomials in my head, and that's, again, something you want to make sure you can practice. So if I square e to the x, that's e to the 2x. If I multiply these two things together, I get, and I'm going to do this at the side, e to the x times e to the negative x. Then I double it. That's going to be 2e to the 0, so that's going to be 2. Like that, okay? And then this next one is going to be e to the negative 2x. I'm going to do that fairly quickly to kind of get past this key point right there. Remember, what you do is square the first, square the last, multiply together, and double. That's the shortcut that we worked on a little bit. Then the second one's almost the same. It would just be e to the 2x, then it would be minus 2, but then it would be plus e to the negative 2x, and then you square the 2, you get a 4 like that. Okay, if you have trouble doing that squaring in your head, write it out twice in FOIL, and you'll get the same thing if you work out the details. So now what we'd have is we already have a common denominator, so I'm just going to put it in one fraction. I'd have e to the 2x plus 2 plus e to the negative 2x, and so you got to change these signs, so you'd have minus e to the x plus 2 minus e to the negative 2x like that. All right, what do you see happening, if anything? A bunch of things cancel, right? Boom, boom. I missed something, didn't I? I missed that. Shoot. Okay, that's an e to the 2x. That's an e to the 2x. So those cancel. Look what you're left with. Looks like you're left with 4 over 4. So we got 1. So we proved it. Okay? So what one of the key things in hyperbolic trigonometry you want to remember is that's called the fundamental identity. Sine squared plus cosine squared x equals 1 is the fundamental theorem in circular. This is the fundamental in hyperbolic. Well, hyperbolas have a minus in it. That's how I remember. It's just x squared minus y squared equals 1. Okay, so that'll get us at least started on this. And then we're going to wrap this up a little bit next time, then. So I'll do this in 2 parts.